Hey space friend, after the second cryo chamber incident, I realized that the ship's AI has got way too much authority here. Some of my critical ship systems are going to need hardware failsafes, so today we're going to use logic chips to confirm my ID is verified, the pressure is safe, and the ship is not on lockdown before the airlock opens. Otherwise, I'm convinced the AI is going to throw me out of it any day now. This is going to give us practice using logic gates to make things happen instead of using any code or software. An integrated circuit, or IC, is a tiny chip that contains a bunch of electronic components like transistors, resistors, and diodes all packed inside. It performs a specific job like counting, storing bits, or making logic decisions. Logic chips are a special kind of IC used to form digital logic functions like AND, OR, NAND, exclusive OR, gates, counters, multiplexers, things like that. There are thousands of these, and they're divided into groups called logic families. Two of the most influential logic families are transistor logic, or TTL, and complementary metal oxide semiconductor, or CMOS. TTL is a logic family built from bipolar junction transistors, or BJTs, which are used to switch and amplify electric signals. CMOS devices have high noise immunity and low static power consumption. They don't produce as much waste heat as TTLs. A very common type of TTL logic chips is the 7400 series. All the basic logic gates are included, plus some of the more complex logical elements as well. 74LS chips are part of the lower power Schottky TTL family and use TTL voltage thresholds. 74HC chips are high-speed CMOS devices and use CMOS voltage thresholds. 74HCT chips are CMOS internally but use TTL compatible input levels, making them easier to mix with TTL systems. There's also the 5400 series, which is a military-grade version of the 7400. These operate over a wider range of temperatures and are great for outdoor devices. Logic gates are core components of all 74 series chips. Each gate takes one or more binary inputs where 1 equals high and 0 equals low, and gives a binary output based on a logical rule. One example is the 74LS00. It contains 4 NAND gates, each with 2 inputs. So it's a chip that just gives you 4 independent NAND gate circuits. Each NAND gate is internally built from transistor networks arranged to perform NAND logic. It internally contains a network of BJTs arranged so the output stays high unless both inputs are high, the definition of NAND logic. Here's a summary table for the differences in the 7400 series of a common assortment kit. LS is low power Schottky. It's slightly older and has good compatibility with TTL logic. HC is a high-speed CMOS family that generally uses less power than TTL devices and is widely used in 5-volt and many 3.3-volt systems. Many of these chips are functionally identical, like the 74LS00 and 74HC00. They just have different tech. For the different types, logic gates are helpful for building your own logic circuits or visualizing digital logic. These are often embedded in PCBs when simple conditions must be checked quickly and reliably without a microcontroller. Shift registers are great for Arduino projects needing more I/O, like when you want to control multiple LEDs from just 3 GPIO pins. Arduino projects and things like retro game consoles or test equipment still use these pretty heavily. Decoders are great for display control, memory mapping, or controlling multiple outputs. Decoders make systems more modular and are still used in low-cost or reliable industrial electronics. Bus transceivers are useful in multi-chip systems to prevent bus contention, where multiple chips try to drive the same data line at the same time and manage shared data lines. And counters are useful for timers, clocks, or pulse counters. In embedded systems, counters reduce software complexity by tracking things in hardware. Here's a summary by the application area. With these logic chips, you can make things happen without any code or a microcontroller required. You can build a purely hardware-based circuit using logic gates only, which process electrical signals directly. Each IC in the 74 series performs a specific logic function like AND, NAND, OR, and so on, based on its input pins, and then produces the output in real time. We're essentially building a program with wires and gates instead of with lines of code. Microcontrollers didn't eliminate these chips entirely, but they replaced many of their roles by combining their functions into a single programmable device. A microcontroller like the Arduino contains a CPU to run code, memory to store the code in variables, I/O pins to interact with things like buttons and sensors, and logic circuits, counters, timers, and more, all on one chip. So instead of wiring up a 74LS90 for counting and a 74LS00 for logic, you can program a microcontroller to do all of those tasks with software. Because these logic decisions happen directly in hardware, they occur extremely quickly and don't require a CPU to execute instructions. Think of it like the difference between a typewriter and a laptop. A typewriter does one thing well and a laptop does way more, but you can't. can't see the gears turning. So these chips are our logic gates, where instead of writing code like if captain ID and pressure safe and not lockdown, we are physically building that decision instead out of electricity. This chip is a 748C08. It contains 4 separate AND gates inside of it. Each of the 4 separate AND gates have 2 inputs and 1 output. The output only becomes high or true if both inputs are high or true. So 1 and 1 equals 1, but 1 and 0 equals 0, and 0 and 0 also equals 0. Now the confusing part when you first look at these chips is the pins, so let's break that down. On the 748C08, every group of 3 pins belongs to one AND gate. Pin 1 is input A, pin 2 is input B, pin 3 is the output, pin 7 is ground, and pin 14 is VCC. Pin 1 starts at the dot on the chip and goes around counterclockwise. A chip like the 748C08 is not one big AND gate. It contains multiple AND gates inside of it. For the 748C04, it contains 6 separate NOT gates. The pins are just inputs, outputs, and power for the tiny electrical gates. On the 748C04, the ground and the VCC pins are the same as the 08 was. In this project, we're using 5 volts to represent high or true, and 0 volts to represent low or false. The chip calculates A and B and puts the result on Y. So internally, the chip is calculating pin 1 and pin 2 equals pin 3. So for the AND gate, I have the LED linked to pin 3 for the output, and the wires for the AND gate are on pins 1 and 2 going into either the VCC or ground section of the power rail, depending on what I want to happen. I also have pin 7 of the chip connected to ground on the power rail and pin 14 connected to VCC on the power rail. This other chip is a 748C04, and that contains NOT gates. A NOT gate is simpler. It only has 1 input and 1 output because its only job is to flip a signal. If the input is high, the output becomes low, and if the input is low, the output becomes high. So NOT 1 equals 0, and NOT 0 equals 1. Now here's the actual problem that I wanted this circuit to solve. The airlock should only open if my captain ID is verified, the pressure is safe, and the ship is not in lockdown mode. So in logic terms, captain ID and pressure safe and not lockdown. Now one AND gate can only compare 2 things at a time, so I can't just feed all 3 conditions into the same AND gate. Instead, I have to break the problem into smaller steps. So first we use one AND gate to check captain ID and pressure safe. Those signals go into pins 1 and 2 on the 8C08. Then the result comes out of pin 3 as a high or low signal, and the LED lets us visualize that output. So now pin 3 is carrying a new signal that says captain ID is verified and pressure is safe. I then connect pin 3 to pin 4 so that the output of pin 3 is the input for the next AND gate. Then on the HC04, I take the lockdown signal and feed it into the NOT gate. That goes into pin 1 of the HC04, and the flipped version comes out of pin 2 where the LED is the output. So now pin 2 is carrying NOT lockdown. The final connection is the really important one. I take the output of the NOT gate, which is pin 2, and connect it into the second AND gate on the 8C08 pin 5. This is conceptually the most important connection in the project because it allows the NOT lockdown signal to participate in the final authorization decision. The ID is verified and the pressure is safe, but lockdown is not active. Connecting 8C04 pin 2 to 8C08 pin 5 is where the NOT lockdown information gets injected into the final decision. Pin 2 on the 8C04 is the output pin, so if pin 1, the input, is high, then pin 2 becomes low, and vice versa. Then we connect the NOT gate output to one of the inputs on the second AND gate. 4 is input A, 5 is input B, and 6 is output. So the green LED is for our first AND gate, the purple LED is for the NOT gate, and the orange LED represents the final output of the combined logic circuit. When we do this, there's no Arduino controlling the logic. We're only using Arduino to power it. The chips themselves are physically processing binary signals using hardware. Each wire is carrying either high, which represents 1, or low, which represents 0. And the logic gates mathematically transform those signals into new signals, which is the foundation of digital electronics. Great, now I've got a hardware failsafe for the airlock so that the ship has to obey digital logic instead of whatever emotional journey the AI decides to be on that day.